Hello, everyone. Welcome to the lecture coinciding with the Chapter 4 in Schmidt and Lee readings. This lecture is titled Sensory Contributions to Skilled Performance. To be successful in a skill, your performance depends greatly on the effectiveness to detect, perceive, and then use the sensory information provided from your environment. Success can also be affected by how well you detect movements in your own body, as well as correct any of those errors in your position. So in this chapter, we will discuss the types of sensory information available for those movements. Then we'll talk about the closed loop process of motor control. Then also we'll talk about how feedback fits into this concept, how our vision plays a large role, as well as how the awareness of our body determines our movements. Two major types of sensory information exist, one that comes from outside the body and then one that comes from inside the body. Exteroreception is how we process information about the state of the environment, therefore the information that comes from outside of the body. Examples of this would be our vision and our hearing. Vision's a huge one. We use our vision to understand how objects are moving around us, how fast things are moving, in what direction they're moving, as well as how fast and in what direction our body, is moving through space. Audition, which is our hearing, is also key in understanding the movement around us and our own movement. I want you to think about when you hear a car engine off in the distance. We have an idea of how fast that car is going, as well as the direction it's traveling, by the sound of that engine. Except for a Prius, of course, because they're quiet and sneaky. Next, we have proprioception. This is the sensory information about the position our body is in space. This is an internal awareness, such as the movement of our joints, our muscles, and the orientation of our body. Our feet are constantly undergoing proprioception when we stand and when we walk. They monitor joint position, they monitor gravity, the lean in our body, the speed of our step, and this keeps us moving fluidly and balanced. So I want you to try something. We're going to use our proprioception for this task. I want you to hold one hand in the air, touch your nose with the other hand, and then close your eyes. Now use the hand that is touching your nose to touch the middle finger of the hand that's in the air. You'll notice that in this task, it's much harder without your vision. Try it again now with your vision and see if you can find your middle finger much quicker. So this demonstrates how much vision plays a part in our awareness of our body. Proprioception is sensed by many receptors throughout the body. In your ear, there is this receptor called the vestibular apparatus. This receptor senses your body's orientation, like if you're right side up or upside down, and it senses your posture as well as your balance. Another type of receptor in your joints is called the joint receptor. This gives info of the joint's position to the brain. These receptors sense if the joint is being hyperextended as to provide limits on your movement. Next, located in the tendon and muscle junction are another receptor called Golgi tendon bodies. These sense the level of force a muscle is exerting on the tendon and where it's connected to the bone. And then in your skin, we have cutaneous receptors. These receptors sense pressure, temperature, touch, as well as haptic sense, which is the vibration of your phones when you touch certain buttons. These receptors send information to the central nervous system, which is basically your spinal cord and your brain. And it's here in the central nervous system that the information actually gets organized in a way to understand the body's awareness. So how does the central nervous system then take this information and determine what to do about it? The central nervous system processes this information in what is called a closed-loop control system. This is when information about the body is sent to the central nervous system. The central nervous system then sends a decision on what to do back to the body. Feedback on how this decision has worked out is compared to feedback on what the central nervous system expected to happen. Then, if an error exists, the information is sent back to the central nervous system to act on correcting that error. The loop goes from body to CNS, back to body, back to CNS, back to body, and so on. It's constantly making decisions on how to move based on constant feedback of the environment and the body's awareness. Closed loop means that there is no end, no break in the circle. Balance while you walk is an example of this closed-loop control system. Proprioceptors in the feet send signals to the brain about the state of the body in the environment. The brain sends a signal to the muscles in the feet on how to manage this state of the body. Feedback is then sent back to the brain from the feet, being compared to what the brain was expecting to happen. If there is an error, then the information is acted on by the brain to correct that error and sends a signal back to the feet on what to do about it. It loops like this non-stop. Here is a figure outlining this process. First of all, there is a desired state of the body in space. You can see that at the top of the figure. The executive system is the central nervous system. It sends a signal to the effector system, i.e. the muscles in the feet, to move to that desired state. Then the body moves, and the actual state it ends up in is sensed by the proprioceptors. This feedback from the proprioceptors is sent to the comparator, which is where it is compared to the desired state of the central nervous system where it started with. So basically, the actual state is compared to the expected state. Then, error in that movement is detected, and the information is sent to the central nervous system to correct. Again, the executive system sends a signal to the effector system to correct that error, and the loop continues on. I want you to remember that conceptual model of how we process information back from the last lecture. Remember, we get input, then we identify the stimulus, we select a response, we plan the movement program, then we generate output. Well, this is an expansion on that model, adding the closed-loop control model to our information processing model. Think of the information processing part as what happens in the brain, the executive system, the 3 stages. And then what happens in the body is the effector system. So after that box that says movement programming, then a movement is generated. The effector system, which are the blue boxes, carries out this movement. Feedback from the environment and from our body's awareness is sent back and then compared to the expectation that was formulated in the movement programming stage. So the actual state is compared to the expected state. Then, if error is detected, that error signal is sent back to the brain and the whole process starts again to correct that error. It just loops like this over and over. Your posture, doing a handstand, or steering a car are all good examples of when this happens while in a movement state. However, sometimes the movement actually has to be completed before any corrections are made. This is in the case in faster movements, where you aren't holding a movement state. For example, it would be hard to sense feedback quick enough to correct the error in the case of swinging an axe. In this movement, you're not holding a movement state, and so the error is typically not detected until the movement is finished, and then you can see if you hit your target or not. So this closed loop control model works for movement states, not the rapid, faster movements. Putting both of those models together illustrates how much we are actually able to alter the nature of our movements that we are producing. We are quite flexible in our execution of action based on feedback. However, as we talked about on the last slide, when the movement increases in speed, or if it increases in complexity, like in our changes to reaction time, this closed-loop system can have limitations. The stages of information processing can be very slow, especially if there's more stimuli or more response choices that we have. This happens in tasks that involve tracking something that is changing quicker than 3 directions per second, such as in a football fumble. This limitation also happens in tasks that are very rapid, with definitive endings, such as in kicking a soccer ball. Like what was stated on the last slide, tracking tasks are one of the limitations to the closed loop control system. So what is a tracking task? Well, it's the task of following some continuously changing target. Research has shown that our information processing system, combined with the closed loop control system, can only make modifications to movements at a rate of about 3 error corrections per second. Now this is pretty quick when you think about it, but certain tasks have changes that are occurring way quicker than that. The example of the football fumble. The ball is changing directions so rapidly that our processing systems can't keep up. This is why we fumble. Every error detected spurs on a correction movement, and therefore this correction movement has to go through the information processing stages every single time. So the closed loop control system is really poor at tracking tasks, and tracking tasks are where objects are changing directions faster than 3 changes per second. Limitations also exist in discrete tasks that are performed rapidly. Generally, most rapid actions are initiated with full commitment to the full planned movement. Therefore, the feedback-based control of movement is way too slow to correct that rapid movement. In the swinging of an axe example, the planned movement is very rapid and requires a full commitment to the whole process. Even if an error was detected, the time it takes to process that error feedback is slower than the time it takes to complete the swing of the axe. Think about the task of typing a text message in a hurry. Have you ever noticed that you realize you're about to hit the wrong letter, but you end up hitting it anyways because your movement is too rapid? This is an example of when the movement is too fast for the feedback corrections to be made. So let's try this ourselves. I want you to take out your phones and start a blank text message. And once you're ready, I want you to see if you can type this sentence as fast as you can. Pause this video and give this a try. All right, how many letters did you mess up? And did you have time to correct yourself before pressing the wrong letter? And how many times did autocorrect fix what you typed? So this is an example of when a movement can outpace our closed loop control system. All right, so moving on. I assume most of you have had anatomy and physiology or currently in that course, but let's go over the central nervous system neuron pathway just in case. There are two types of neurons that exist. One takes information from the receptors in the body to the spinal cord and brain, and the other takes the information from the spinal cord and brain back to those organs in the body. Afferent neurons travel from organ to the central nervous system, and efferent neurons travel from the central nervous system back to the organs. So when something is sensed in the receptors of your skin or your inner ear, the signal is sent via the afferent neurons to the central nervous system. Then when the central nervous system makes a decision on what to do about that signal, a message to make an adjustment is sent back to the organ via the efferent neuron. In cases where the information processing system is required, those three stages, there are multiple neurons that synapse with each other along these two pathways. And typically, there is a representative center in the brain that does all of that information processing. Now, in the case of a reflex, this pathway bypasses the travel up to and back from the brain and does an automatic synapse from afferent to efferent neuron just within the spinal cord. This reduces the time it takes from sensation to movement significantly. We don't think much about a reflex. It just happens. Very little, if any, information actually gets processed in the brain during a reflex. Proprioceptive reflexes exist in the body where the closed-loop control bypasses the information processing stages. An example of that is the knee-jerk reflex. I'm sure all of you have had this done in the doctor's office when you were a child. So let's watch this video on how this reflex works. Two types of reflexes exist. The knee-jerk reflex is an example of a monosynaptic transmission. Only one synapse happens between the afferent and the efferent neuron. This reflex happens without any thought at all. The slightly slower multisynaptic transmission is the second type of reflex. This information passes through more than one neuron and synapse, but still arcs in the spinal cord to generate a quick response. The information travels to a higher level of neurons, however, ones that sense pain and create memories, which slow down this reflex just a little bit. But still, the stages of information processing are skipped. An example of this is when we touch something very hot but pull away quickly. We are aware of the pain and can remember the situation later, but we did not go through the feedback-based process. Basically, a reflex skips the three stages of information processing in the brain. Here, these two reflexes are added to our conceptual model. M1 represents the pathway of the monosynaptic reflex, and M2 represents the pathway of the multisynaptic reflex. The knee jerk is the example of M1, and the withdrawal from touching something hot is an example of M2. Reflexes happen with no information processing and no feedback correction processing. This is why you'll see the pathway of M1 and M2 skipping the executive system and only traveling through the effector system. All right, let's move on to vision. Our vision, of course, has a very important role in everyday activities, and those who have impaired vision have a much harder time functioning in life. Vision is considered exteroreception and not proprioception, and so the reflexes will differ. Visual information is delivered from the retina of the eye to the primary visual cortex in the occipital lobe in the brain, then along two separate processing pathways to other different places in the brain. These two pathways are used differently in the control of our behavior. The first pathway is the dorsal stream. The dorsal stream is used specifically for the control of movement within the visual environment. It's responsible for the question of where things are around us. Research has shown that the dorsal stream is considered non-conscious, more like a reflex. That is, it's inflexible to change once the movement is occurring. The other pathway is the ventral stream. The ventral stream is used specifically for conscious identification of objects that are in our visual field. It's responsible for the question of what things are around us. So the dorsal stream processing answers the question of where things are around us and is considered non-conscious. And the ventral stream processing answers the question of what things are around us and is considered conscious. Again, the ventral stream is our processing pathway that is used for conscious perception of what things are. And because of this consciousness, this stream uses the stages of information processing, which are stimulus identification, response selection, and movement programming. We know now that the stages of information processing slow down our movements quite a bit. It's not like a reflex, where the transition to an efferent neuron happens at a lower level of the central nervous system. This stream plays a role in our movement control by allowing us to make a conscious decision of what action we would execute. For example, if we wrongly identify an object, our movement to avoid that object could have serious errors. If that object was an oncoming car, the failure to identify it could result in an accident. The role of the ventral stream in movement is also affected when the lighting is dim or dark, and we are less able to identify things. This affects our movement greatly. It could slow down our movements or even cause us to make errors. Where the ventral stream focuses on specific objects and their identification, the dorsal stream uses the entire visual field to create a picture of where we are and relative to all of those objects in our environment. This stream specializes in movement control, such as balance, or the direction we should move in our space, or the time it takes for us to reach a destination in our field of vision. The stream is considered non-conscious, as it is more like a reflex rather than conscious decision about how to move. It's more like awareness. This pathway in our brain is why we react to things coming at us or when an obstacle is suddenly put in our path. It's a quicker control of movement than the ventral stream. Let's say you're a football player out on the field in the middle of a play. There are many things going on around you that you have to quickly judge and then respond to. You will have the path of travel of your teammates, the path of travel of your opponents, the ball that is flying through the air for you to catch, and in the path of travel you will run to catch that ball. The dorsal stream is what allows you to gauge how fast and far you need to go to catch that ball, and which direction you should move in order to avoid your opponents. The dorsal visual stream, along with our proprioception, is also what helps us maintain our balance. This is why it's much harder to balance on one foot with our eyes closed. If we go back to our conceptual model, the ventral stream would be within the pathway of the outer loop. So it's not represented on the slide because the outer loop is already there. An object will be visually identified, a response will be selected, and movement plan will be made. Then the movement will be executed as information sent from the brain to the spinal cord to the muscles. Proprioceptive and exteroreceptive feedback will cause us to loop back to compare that feedback to what our brain was expecting us to do. Any error found will be corrected and executed as another conscious decision. That's the ventral stream. In the case of the dorsal stream, however, the blue arrow is added to our model. Because this is more reflex-like and non-conscious, the visual exteroreceptive feedback of our environment will travel to lower parts of our central nervous system, where it synapses quickly with an efferent neuron for quick execution of movement. Again, our balance is an example of this. Another example is riding your bicycle through traffic, or riding your bicycle in a parking lot full of cars and people. Again, these are examples of when our dorsal stream is being used and kind of just refers to our awareness. All right, the last thing we're going to talk about is audition. Auditory feedback and motor control. Audition is rather understudied compared to our vision, and therefore it's a bit vague on how auditory information is processed in the central nervous system. We don't really know if there are two streams, such as the ventral and dorsal in our vision, but what we do know is that disruption to audition can cause errors in our movement, basically indicating that audition plays a large role in our motor control. For example, if a speaker in the front of a large auditorium is talking through a microphone, he or she will typically hear their voice as a projection through the speakers in the back of the auditorium. There is delay in when the speaker talks and when they actually hear their voice. This can cause timing errors that wouldn't normally be there if the speaker did not use a microphone. They may have delayed speech and longer pauses between sentences. This also happens when playing musical instruments on a stage through a sound system. This is why a feedback monitor is typically placed on the stage right by the speaker or the musician so that they can hear their sounds in real time. Our vision, however, is more dominant over our hearing and will actually override our movement control even if it's incorrect. An example of this would be an outfielder's position in baseball. The sound of a correctly hit baseball on the bat is quite distinguishable from the sound of an incorrectly hit ball. Let's say the batter hit the ball incorrectly and made that specific sound. If the outfield, however, sees the ball leave the bat and identifies it as a line drive, which is an incorrect identification, the outfielder might decide to run backwards, anticipating that line drive, whereas the ball is actually a slower grounder that would require running forward to it. So this is when vision, even if incorrect, can override correct auditory information. So basically a recap: audition. Disruptions to audition can cause errors in movement. An audition will be overruled by visual sensation, even if that visual interpretation is incorrect. Okay, so this concludes the lecture on the sensory contributions to our motor control. Please feel free to listen again, pause where you need to, or email me if you have any questions about any of this content. Thanks for listening.